Standard medical models categorize severe neurodevelopmental states, ranging from the autistic spectrum to locked-in syndromes, as irreversible structural brain damage. The assumption is that the internal circuitry is physically broken. This structural model is complicated by a documented clinical anomaly known as the Zolpidem paradox, which points to a different mechanical reality. In specific cases of severe brain trauma, patients administered the common sedative Zolpidem miraculously regained speech, motor control, and cognitive function for a few hours. This poses a logical problem for the structural model. A temporary chemical sedative does not have the capacity to rapidly rebuild destroyed neural pathways. From an engineering perspective, the underlying hardware governing speech and logic must be intact, currently buried under an overwhelming floor of internal noise. The processor is currently trapped in a high-gain defensive posture, where the sensitivity of the circuit is turned up so high it jams the logic gates. If the hardware is persistent, these severe states may be failures of available processing headroom rather than permanent structural damage. This graph illustrates the mechanical mechanism of signal saturation, serving as a primary model for understanding the locked-in or autistic state. Internal biological noise, driven by excitatory chemicals, raises the baseline noise floor until the clean signal is forced against the absolute limit of the system's capacity. We define this flattening event as voltage clipping. The incoming sensory data hits the physical ceiling of the hardware. When data clips, it generates harmonic distortion. For the user, standard environmental inputs like lights or distant sounds become painful, high-amplitude white noise. This is the root of sensory processing disorder. The brain compensates for this internal static by injecting repetitive physical noise, stimming, to ground the chaotic interference and establish a predictable spatial signal. Effective recovery requires moving past behavioral training to a hardware-level calibration designed to manually turn down the system's gain. Behavioral therapy cannot teach a clipped processor to handle a signal it cannot see. The system's physics must be recalibrated to lower the noise floor before higher-level processing can resume. We model the brain's processor as a CPU triad, an integrated neurovascular unit consisting of microglia, astrocytes, and the insulated neuronal bus. Node 1, the microglia, serves as the system's dedicated security logic and maintenance drones. During a biological impulse event, like an infection, the microglia flip into an M1 attack state to protect the hardware. The primary failure occurs when the system enters a hysteresis latch, a state where the microglia remains stuck in this high-gain defense posture long after the initial threat is removed. Locked in defense mode, the microglia abandon their critical background optimization task, synaptic pruning. Without pruning, the neural architecture becomes a dense rat's nest of redundant, unoptimized, and poorly insulated wiring. This unoptimized network results in massive signal crosstalk and logic data paths. The structural rat's nest keeps the processor perpetually overheated, jamming the logic gates and making complex social or sensory data processing impossible. Troubleshooting a latched system requires identifying the source of the continuous noise that keeps the microglia in their attack state. The noise origin is often located off-site, down in the body's power and logistics hub, the gut microbiome. A supply chain breach, clinically known as leaky gut, allows foreign particles to escape the intestinal barrier and enter the transport stream of the systemic circulation. Pathogenic bacterial overgrowths within the logistics hub generate specific toxic byproducts known as endotoxins. These endotoxins, specifically lipopolysaccharides or LPS, act as potent biological electromagnetic interference. This interference travels directly up the vagus nerve, the system's main data bus, injecting high-amplitude static into the brain's processor. This upward surge of dirty current physically jams the bus, preventing the brain from receiving the all-clear or parasympathetic brake signal. As long as the logistics hub pumps dirty current into the neural bus, the security logic will remain latched, rendering top-down psychological interventions ineffective. The technical stack is an engineering protocol designed to restore function by stabilizing the hardware environment. Standard dosing fails because the brain is a black box. Immense hardware variance in genetics, impedance, and thermal limits requires individualized, iterative inputs. The first step is installing a signal pad. Metabolic current limiters like inositol are deployed to artificially lower the systemic gain. By reducing the amplitude of intracellular signals, these metabolic limiters prevent the voltage from hitting the hardware ceiling. Padding the signal immediately halts the sensory clipping, providing the processor with the functional headroom needed to decode sensory data. This stabilization doesn't clear the root cause, but it establishes the system integrity required to attempt a deep clean. Attempting to clear root pathogens without first establishing a signal pad risks triggering a catastrophic hardware crash. With the system padded, we execute the active flush, the industrial debridement of gut biofilms to cut off biological interference. But this debridement carries a severe risk. Breaking down the biofilms suddenly releases an acute, massive surge of dirty LPS current. If this current hits the processor unmanaged, it breaches the system's thermal limits, causing a system trip that manifests as behavioral meltdowns. We manage this risk through iterative titration, a control loop adjusting every input based on real-time telemetry. Behavioral spikes become diagnostic trouble codes, informing the use of internal coolants, like NAC, to act as a heat sink for the purge's thermal shock. Once the interference is flushed and the cooling system holds, the internal noise floor drops below the critical switching threshold. The hysteresis latch breaks, and the microglia finally flip back to the M2 repair state. These maintenance drones resume synaptic pruning, systematically clearing away the rat's nest to restore optimized wiring. By closing the logistics gate and lowering the noise floor, the brain's inherent logic emerges from the static, restoring the system to high-speed laminar flow.